for ammonia synthesis. I think briefly we discussed about the scale up, plasma, how easy, how difficult scale up. But I think there's one slide I want to share. It's not finished. Okay, I think last slide. All right. So if you see this slide, so this also talking about the cold plasma. So if you look at it, the device, I mean it's pretty simple actually. If you look at, they can use the plastics and then cross tube or glass tube to basically make the device. I mean, to put this way, microwave. I don't know how expensive the microwave you purchase. So microwave I purchased costs somewhere from $60,000 to $100,000. It's difficult to build a laboratory. I have 8 microwave reactor, large and small. That totally cost me probably over $1 million. Now, if you do the cold plasma, it's easier to start. Probably the $20,000 you can start it, and then it's easy. You can see the device very easy. It's kind of trade-off. I mean, it's easy entry, but when you get into the scale up, then you have to think about it. How I'm going to scale up the reactor. So I want to make a point here is this basically shows you the different way to run I would say the plasma. So there's a plasma, you can run the DBD, generate the plasma, but this cartoon really shows you run the plasma and then the oxide, then you feed in that plasma in the electrode chemical reactor integration. The whole setup, and this actually is the real picture on the bottom. It's basically it's pretty easy. You have DBD plasma and also electrical cell, and then for the graduate students or the folks audience interested in the plasma, I would say that maybe cold plasma is somewhere you can start. It's easy. It's a low cost. You can start it. But once you learn enough, then you can go to the microwave plasma, because microwave plasma is going to cost you money, especially if you deal with the so-called different power and also different frequency. I have variable frequency the plasma in my laboratory. So if you change the frequency, and then it costs a lot of money. But I would say cold plasma like DBD or any other like a corona discharge, they're not has nothing to do with the frequency. It's just the voltage. But as long as you keep safety, the setup is very simple. You can see on the bottom of this one. It's easy entry to learn for the beginning the researcher. Okay, that's the point I try to make. So anyway, any question here on the scale up for the plasma or the cold plasma, microwave plasma? Any question before we move to the catalyst design? Okay, we are good. So let's go to the catalyst design. All right. So innovation in microwave successful catalyst design for ammonia. So before I talk about the catalyst design, I'm talking about the heterogeneous catalysis. That means the catalyst is the powder, is the material, and then you synthesize in the laboratory, and then you design catalyst, you synthesize, put in the microreactor. I'm going to ask the question: how many the student or any student in the audience have ever synthesized the catalyst for anything? It doesn't have the ammonia for any of the reactions. Do you have hands-on experience working in a lab to make a catalyst? It's very important because it depends on how deep I can go. I can go through my lecture notes. Just raise your hand. No, I never seen the catalyst. You can say, oh yeah, I make a catalyst. Can you give a microphone to anybody who even see the catalyst or how to make a catalyst in the laboratory?
Yes, sir. We have synthesized catalyst, sir, for different processes for biodiesel production for pyrolysis.
Oh,
So
good.
synthesized catalyst for many applications. Recently, we entered into catalyst synthesis for ammonia production.
Okay, very good. So now you made me feel comfortable. So now we talk about catalysis. Okay. So basically let me go to thank you. So basically talking about catalyst. Okay. So this is very basic. Catalyst for the any reaction. I mean I'm talking about heterogeneous catalyst. Homogeneous catalyst is different. Okay. I'm not gonna focus. So pretty much for you mentioned about pyrolysis, is that right? For methane pyrolysis or hydrocarbon pyrolysis or ammonia synthesis, it's a heterogeneous catalysis.
Yeah, it's heterogeneous.
Heterogeneous, okay? So some students may not understand what I say. Okay, so heterogeneous catalyst, okay? So basically heterogeneous catalyst is nothing but support, which is here, and the metals. Okay, so this is the metals. Traditionally, people believe, for the ammonia synthesis, it's the same. Let me back up. Support provide you infrastructure, which is the physical structure, like see in this imaging. So there's a surface area, porosity, which allow the metal anchor on the surface. But I draw a flat surface. In reality, it's not flat. It's more like this. Okay. So basically, you put the metals onto this porosity. Then because of it's larger surface area, and then the molecule can diffuse, react with the metal, come out. So traditional heterogeneous catalysis is providing surface area and then allowing the metal enter. The larger surface area, the more the catalytic surface. All right. So on the right hand side, you see another different support material. It's called the zeolite. Okay, zeolite. Basically, zeolite has a high surface area, like 400 square meter per gram, and then you can put the metals on the surface, catalytic reaction. So this is a picture of the real support material. This is zeolite, and then there's a support material, and it's called heterogeneous catalysis. But for some reaction, the surface area may not be not important because it's electronic fact. Electronic fact means catalysis is nothing but you have the electron donate to the molecule, make that bond vulnerable. So for simplicity, for nitrogen bond. I don't have the formula to draw. It's basically between nitrogen and triple bond and not single bond. Okay, so nitrogen triple bond is very stable. In order to make unstable, the nitrogen get on the surface, they have to share the electron. So electron has to move to the nitrogen in order to make that triple bond vulnerable. Then you can break the bond. Okay, so that's the catalysis. So in the ammonia synthesis, it turns out surface area is important, but it's not as important as the electronic effect. So it's called reduction oxidation process. So it's called redox process. Redox means reduction oxidation. That means you constantly you reduce it and you oxidize it. Okay, so that's the traditional process. Okay, this is the background how you design catalyst traditional way, and what so ammonia synthesis, physical property versus electronic property. So the question is the physical property important or electronic property important? Over the years, people learn this from experience because catalytic synthesis, there's a science behind, but there are a lot of art. Art means it's more like you cook at home, all right? Cooking Indian food, cooking Chinese food. So because when you're cooking Indian food, it's nobody you will have a recipe 1, 2, 3, 4, 5. If you follow recipe, one student in the audience follow recipe, the other student follow recipe, you cook can be different. You agree, all right? Even if you follow same recipe, Indian food, same ingredient, if you have two separate students cook it, they are different. That's what happened in the catalyst world. You follow the same recipe, you synthesize, even you follow the literature, you may end up different performance. Okay, so this is the challenge. But true, there's science to follow. Today I'm going to tell the science part of the catalyst design, not the experience, because experience it depends on how you practice. But there are science part of catalyst design and synthesis for ammonia. Okay, so today's science, not the art. Or art part is kind of difficult. That's why I always in a in a conference I always joke with the audience. I say, hey, catalyst is different from other like a semiconductor. Okay, so catalysis means semiconductor. You have a design, everybody end up the same as long as the design is the same. But catalyst, you have a good design, you may end up differently when you cook it or when you synthesize at in your laboratory. That's why I use the cooking at home as a good example. Okay, so now I'm talking about the physical property versus electronic property. This is the science behind which one is important. So let's take a look at what's the commercial use. Remember I told you these two gentlemen, Haber and Bosch, in their early days in the 20th century, between from 1901 to 1909, 8 years, they actually screened 4,000 formula. When you screen the formula, each formula has to go through testing, all right? So that means you make a catalyst in the microwave world. You make a catalyst, let's say you put into this is the wafer, you test it, doesn't work, go back again. It's all the work. It's not like you make a bunch of them and then it's successful. That's why the Haber Bosch made 4,000 formula. They probably run 40,000 experiments because each formula may run the 10 tests. So it's very exhausted. Then they came up with this catalyst. Okay, that's what you use today. Over the 100 years, when you talk about Haber Bosch iron catalyst, the composition is still like this. It's just a matter of which one is more. It's a mixture of iron oxide, FeO, Fe2O3, Fe3O4, but the component doped with potassium and doped with magnesium oxide. Today, the top, the Holder Topsoe, KBR, and then all these big catalyst companies, they are still making this. They always have the secret sauce, but nothing about this formulation. It's just a matter of percentage differences. Why you have the 3D iron has a different oxidation state to have because the reduction oxidation process during the reaction, the electron has to be shared between catalyst and the nitrogen. That's how you activate the bond. So this potassium magnesium oxide is called a promoter. You can see they are alkali, all right? Alkali promoters help to donate electron, and then the constantly the oxidation state change between this metal oxide help the electron shifting. Okay, so under the temperature pressure, the activation of nitrogen taking place. Okay, this is a traditional way to design the make catalyst. Keep in mind, in the old days, 100 years ago, there's no design tools. They don't have anything like XRD, SPS, whatever, and TEM, SEM. They don't have those fancy tools. And to show today, what we have is so today we have this. It's called STEM. You can see the microstructure. We understand how the micropores start. But 100 years ago, they have nothing. All they have to do exactly what you cook at home. Practice. You learn from your mother, learn from your grandma, you learn from your mother. That's all you are doing, cooking for 100 years. But now today different. There are science behind. We are going to design the catalyst. Make sense? Any questions? Okay. So keep in mind, when you design the catalyst, you make it in laboratory, you have to do the testing microwave. Okay. You may ask me, how would you design the microwave catalyst? I show you this before, all right? Keep in mind, microwave susceptibility or microwave sensitivity is very important. When you design catalyst, do the formulation. What kind of metal oxide in there, what kind of metal we put in there. You had to worry about the dielectric loss and the conductive loss and the magnetic loss. Okay, so the 3 different properties dictate your activity under microwave. Magnetic loss, I mean, the advantage of the magnetic property is because of the iron oxide has this magnetic property. Most of the time in our formulation we have an iron in there, but not necessarily using iron. There's another metal called ruthenium, Ru. I'm going to show you. They are very active. It so happened ruthenium, if you look at the external orbit, that electron is so easy to donate to the nitrogen, and it's much more easy than iron. Over the year, people found out, I mean, all the periodic table, I think over the 100 years, researchers and the industry company, we screen them all. So it's a lot of effort put in 100 years. So that's why to find iron for ammonia or to find ruthenium from ammonium, it's not a random luck. It's not because, oh, I'm so lucky. No, it depends on years the design. Anyway, so we basically, when we design this, the microwave sensory catalyst, we do not start from scratch. We are not going to try every element in the periodic table, but we do have some kind of guidelines. Basically, those properties has to be sensitive to microwave. Okay, so that's the background of our design. First, I'm going to show you what basic effects of support. Remember, in term hydrogen catalysis, support is important. It's a metal support interaction that enabled activation of molecule. Okay, you have to have a correct metal, correct support interaction in order to activate the nitrogen triple bond. So what we did was, first we started the support effect. So this data really shows the support effect. The support material is the magnesium oxide and also silver oxide. Okay, so the two different support. So you may be wondering, why don't you use the alumina, which are high surface area? Yes, we tried alumina. It's not run to select the magnesium oxide and silver oxide, whose surface area much lower than alumina. There's a reason, because we tried, it didn't work. That's why we came up with a conclusion that for microwave catalysis, the important thing is not surface, it's not physical surface area, is the electronic property. So magnesium is a base. Silver oxide is very unique. Okay, so the silver oxide actually has the unique. Basically, they have two different oxidation states. Here is 3+, and they have here 4+. So the silver, even if in metal oxide form, they have different oxidation states. Whereas the magnesium oxide, they only have the electron donation tendency because of the alkaline nature. Okay, so now we basically make the catalyst using the ruthenium as the metal. We didn't change ruthenium. True, ruthenium we learned from the literature, and then we basically run make the different catalysts, and we dope the potassium and cesium. Anyway, so obviously the activity is different. If you look at this blue bar, the support material is a silver oxide and then the ruthenium, but it has to be doped with the cesium. Without the doping the cesium, and then you can see the activity is not there. Okay, so and then cesium is better than ruthenium. If you compare this blue bar and this blue bar, cesium and cesium is better than the potassium. So anyway, so there's a lot of work behind this. So then you may be asking, what's your design concept? Well, here's our design concept. So we have to do the DFT modeling work. So we basically design a catalyst and then the different formulation. So we basically say, okay, let's build the magnesium oxide and then having the different ruthenium particles on the surface. Okay, actually, this is one of my postdoc to him Ken. I think he got a PhD from the IIT. Now he works in the national laboratory. So he stayed in my laboratory for a year. So he designed this fantastic DFT modeling work, helping us to design the catalyst and make a projection what catalyst is going to be. So this is basically based on the magnesium oxide, and then we dope the ruthenium on the surface, and then see how they perform in under the DFT. Okay. So another catalyst design. Remember, we have silver oxide, and also we also build the ruthenium the different particles clustered on the surface. See how good we distribute the metal on the surface that will enable the activity. There's a lot of the simulation going on. We publish it in the Chemical Engineering Journal. You can track the publication. It's very detailed DFT modeling work, but I only want to show you a result. So maybe let me pause a little bit. Anybody knows anybody understand the DFT modeling work, or anyone has DFT modeling work? I want to speak a little bit about the DFT to the audience using your language, using your own word. Can you give the microphone? If nobody raise hand, just tell me no. Then I will interpret to you. If somebody has the knowledge on the DFT modeling work, just tell me what's the DFT modeling work.
We are using ANSYS fluents for specifically we are using for modeling, sir. But we are not using for chemicals, but we are using to design our mini channel heat sinks and for heat exchangers like
So not for the chemical reaction. So it's the DFT modeling for what? For some atomic property. What do you use for DFT modeling calculation?
We give the proper material properties and fluid flow.
So you use DFT to calculate the property, not do the DFT the modeling work to model the reaction. All right?
Okay. Yes, sir.
Okay, at least you know the DFT, the principle of DFT. Okay, that's good. So that helped me. It's easy to interpret it. If you look at so first we have data here. Okay, so now, but this data is limited data. We can only make this blue bar is basically a silver oxide support, and then the red bar is magnesium oxide support. Even 8 different formulations we test many times. It takes my students several months to get the data like this. There's no way we can end this. So now we say let's take the data and then run the DFT modeling. Just see what the DFT tell us the theory behind it. Okay. So when we run the DFT compared with the magnesium oxide, silver oxide, we begin the same energy state in the DFT. Let's begin the same, and then let it drop. So basically, we start from a single item. You heard about single item now, right? So single item means, and then we began the 4 ruthenium on the surface, each of the cluster, and then we have ruthenium 13, then we have ruthenium the bulk. So what does it mean? That means when we design the catalyst, we want to know how much we allow the ruthenium on the surface, either the single item or the cluster. That means will basically help us to distribute the ruthenium on the surface. Okay, so then we did a DFT calculation and then see on the 2 different supports how the ruthenium behave. Okay, single item is difficult to make. We can make a ruthenium a couple of the items on the surface, or we can make a cluster. True, making big ruthenium particles is very easy. Actually, it's failed. So what does it mean? Okay, so this basically tell you the difference. Let's say the difference is if you begin the single item, let's make them safe. This green bar basically shows that the magnesium oxide on the magnesium oxide surface, this is basically what you call that the green color, that's the magnesium oxide. So keep in mind the lower the free energy, the better. If you compare the, let me make a point, okay? So it's very, that's why I asked the audience if you have a DFT modeling experience. It's a very powerful tool if you understand the theory behind. Okay, I'm gonna let you to look at this part, okay? So constantly you see the magnesium oxide at the same particle size, the free energy is lower. That means it's stable, which is good. So that means, so that means not good. It's a, so magnesium on magnesium oxide, if ruthenium particles are big, it's basically the free energy is lower. To say different way, if you put ruthenium on the magnesium oxide, the ruthenium particle, they tend to agglomerate. Follow me? That means they get together. So they get together, make it stable, because the DFT modeling tell us the molecule, the atomic, the force push them together to become stable. So the point I try to make, when you put a lot of ruthenium on the surface, they are not going to stay in a single atom state. They are on the magnesium oxide, they are going to stay in the agglomerate. Relatively, if you look at on silver oxide energy is higher, all right? So what silver oxide says, okay, if you put a bunch of ruthenium cluster on my surface, silver oxide, I don't like it because I say my energy is higher. So because the different one, so basically silver oxide say differently from magnesium oxide, I don't like this cluster on my surface because you know you stay in the lower energy, but my energy high. So that means, to say different way, if you have ruthenium on silver oxide, they tend to move to the different direction. They want to stay in the either single atom or the highly distributed. You have to interpret differently. I apologize if you don't understand what I'm saying, but that's the conclusion. Conclusion is, on the silver oxide, ruthenium tend to stay in the highly dispersed. And then on the magnesium oxide, ruthenium tend to stay in the agglomerate. So that's what DFT tell us. Okay, there's a lot of theory behind. So based on this, we basically have a different approach to distribute the ruthenium, and then we came up with. Hold on, I'm going to show you this. Okay. I need to go back to the. So basically, oh, I still have this. Let me do. So basically, we run the ST. You know, we compare this black dot. the light, the gray background, they are the support material, either magnesium oxide or silver oxide. This black dot, they are basically the ruthenium on silver oxide. You see these big particles? They are the ruthenium on magnesium oxide. Okay, they tend to go be. So that theory really holds. So that tells us on the silver oxide, we have to make sure the silver oxide distribute in as smaller particles. Okay, I'm gonna stop here. I think sometimes if I don't see the response from the audience, I get annoyed because I mean it's a waste my time to interpret the detail. Let's move on. Okay, so all right. Okay, let's go to the different design. So let's design concept. So to summarize our design concept, so we basically I like to go back to my going on here. So basically, we to design the microwave susceptible catalyst, we have to watch the three properties. We measure the property. There are different ways to measure property. You can measure dielectric property, conductivity, and also magnetic property. There's two you can measure. It's called network analyzer. So once we have to do that, we do the initial. Oh gosh, I'm sorry. I really want to kill this the full screen. I cannot because I cannot write on my screen. That's my problem. I need to write on my screen, but I cannot. Okay, let's stay this way. I think my computer has some problem. I cannot go back, escape, go back to the small screen. So I have to go this. Okay. Okay, we talk about this, and we talk about this. We talk about this already. So let me tell you what you may be wondering. So after we have done so many testing, so what's the next we are doing? So currently we are doing the catalyst reactor design, the microwave reactor and catalyst design. I'm going to spend the probably remaining time just to talk about the reactor design concept. This is one of our the proposal. Why when we design the catalyst, we have to put the catalyst design and reactor design together because they are go together. So in the modern the catalysis, you cannot segregate the catalyst design and then the reactor design together because they are all commingled. So what does it mean? You catalyst put in the reactor, they have to get a sensitivity from the reactor, which is microwave, or your microwave has to enable the catalyst. So this cartoon really shows it's catalytic membrane design. We have catalyst and also for the methane and nitrogen conversion together. So we produce ammonia and also benzene, toluene, and xylene. And then when we design the catalyst, okay, now I'm showing you the microwave. Did you see the microwave? Microwave basis as a wave. There's wavelength, all right? So microwave wavelengths depend on the frequency, and then it has different wavelengths. So on this cartoon, traditionally you just coat catalyst on the membrane, just like this. You coat catalyst on the membrane. So I probably let me start. So this inside the membrane, and then we coat the catalyst. This is a catalyst, okay, on the membrane. It's catalyst. So then when methane come in, the methane dehydroaromatization form the BTS. This basically is the. That's why I want to go back to my screen. So give me 30 seconds. I want to kill this screen so I can go back. I don't know what's happening with me because I can't type. Okay, I want to see what's going on with my present PowerPoint. Okay, now I'm good. Can you see my screen now? Can you see the catalyst now?
It's
Okay. So I'm not gonna go back to full screen because the full screen really pain. I cannot. True, this screen is a little small, but I'm sorry that I have to do this because I have to write the equation. With the full screen, I cannot. Okay. So basically so on the shell side, when methane come in, they form the benzene, toluene, xylene. This is benzene. Okay, from benzene, toluene, xylene. Hydrogen produced going through the hydrogen membrane and go inside the membrane and then react with the nitrogen on the in the core side. All right. So this is called catalytic membrane. So the key is when we design the microwave catalyst, we coat catalyst inner, but that's not enough. Remember the microwave passing through the reactor, there's a wavelength So you see the microwave basically is oscillated, all right? So for example, here, okay, I would say here is, let me get a different color. Yeah, it's easy to teach in the laboratory, in the classroom. I can draw on the blackboard. But now teaching in the online, there's not enough tool to draw the something. Okay, I'm gonna do this. Okay, so basically, microwave passing along the tube, all right? So they basically watch what I do. Okay, so they basically like this. Follow me. So there's a place microwave is very strong, and there's a place microwave is low. All right. So that means microwave interaction with this membrane surface, basically like a high intensity, low intensity, high intensity, low intensity. It all depend on microwave. So based on the frequency, the wavelengths of microwave. Do you understand what I'm saying? So. So this is the advantage of the microwave membrane design. So if you follow what I said, the microwave passing through along the tube, on the membrane tube, different part of the membrane tube see different intensity of a microwave. I'm repeating. Different part of or along the lines of a membrane, different locations see different intensity of a microwave due to the wavelength of microwave. Are you agree with me? If you agree with me, now, so basically see this wave passing through, there's a high intensity, low intensity. So that means along this line, we can put catalyst at a different location. That means active catalyst we put on low intensity, and then the low activity put high intensity. So you may be asking why? Because the microwave is exothermic reaction. You don't want to generate heat at hot spot. So that means if I see the location where the microwave wave intensity is high, on purposely I put a low activity catalyst in there. When I see this the valley, I put a high activity catalyst in there. So I basically even out the microwave effect. So the hot spot is not being there. So the question is, how would you make a catalyst in laboratory? At the beginning, I asked everyone if you think the catalyst. Yes, you think the catalyst. When you think the catalyst in laboratory, you think the powder, you wash coat, all right? So how would you place the catalyst, different catalyst at a different location? What's the answer? 3D printing, all right? So that's what we are doing today. So 3D printing enable us to print catalyst at different location. So basically, you program the 3D printing, and then trying to have the catalyst and a different print at different location. Once you print it, then you have a microwave come in, you test it, make sure, and then basically there's a in situ measurement. You can see a different location and different activity. Make sense? I'm going to do the pause here because I know the audience are getting puzzled. I want to open for the question before I finish today. Anybody understand the concept on the catalyst design and then with the reactor design altogether for microwave? Please ask questions. Otherwise, I don't know what I'm going to talk. Yeah. Anybody has any questions? You have to ask me the question so I can get a sense feedback if you understand what I'm saying. Yeah.
We have a question.
Go ahead.
Yes, sir. I have a basic question that microwave we are talking about, the fusion, no? So here, what I understood is, it will not, it will give the heat energy through electricity. Am I right or wrong? So we are giving the electricity, so the microwaves will be formed, so that it will be giving the thermal energy for the catalyst to interact with the molecules, so that it will be easily formed ammonia actually. So here, what my question is, so we are having the DFT analysis, that is a density functional theory. So when I gone through that results, we are having the microwave and we are having the rhenium and we are having the magnesium and cerium dioxide. So
Okay.
there are different results we have got. So why so? We are having only that microwave, then ruthenium. So there lot of divisions are there in the ruthenium. So and that energy levels also are totally different.
So okay, so now you are okay. You are not. You don't have. You are not asking question about this diagram. So you are actually asking question about the basic the design of the ruthenium. What do you call that? A basic design on ruthenium on silver oxide, and then the ruthenium on magnesium oxide. All right. So why? So you say that you have when you make them ammonia catalyst, you get a different result. Is that correct?
Yeah, that slide number 8, I think.
Slide number 8.
8.
This one.
Yes, sir.
So what's your
So
what's
here the energy level is different for the ruthenium particles actually. So here we are having magnesium oxide as well as cerium dioxide catalyst or there. With the application of microwave, why it is so different for that with respect to the energy level?
well, okay. I tell the truth. I could not hear you clearly. I'm guessing your question. Okay, so I may not give a correct answer because your microphone has a feedback. I cannot understand your question. Since you talk about this, I can only see you have question about this slide. This slide
Is,
is DFT modeling work. The
is
objective of the DFT modeling work, we want to see on the magnesium and the silver oxide surface what particle size are needed. That's the objective of the DFT study. So we basically run the DFT, we found out that on the magnesium oxide, you have no, if you put a large particles, actually you have no problem. If you put a large particle on silver oxide, you have a problem. That's the conclusion, all right? So that made us believe if you choose silver oxide, we have to use the small particles in order to write. You have to see different angle. DFT is relative. DFT will not give you absolute value. DFT, you have to do the comparison. So that means magnesium oxide is our baseline. Green is our baseline. When we are trying to promote silver oxide. So we want to see on silver oxide the surface and what kind of particle size we need. So the conclusion is we should not go through the large particle size because the energy is higher than magnesium oxide, which is baseline catalyst. Did you get my question? Did you get my is my answer your question? Answer your question?
yes, sir.
Yeah, it's all about the particle size, what you need. Because based on this data, we say, okay, on silver oxide, let me put it this way. This data shows you have no problem.
It is bulk. It is going on increasing the surface area, so that energy level is high. I understood.
Surface area doesn't play any role here because in here, magnesium oxide surface area and silver oxide surface area, they are different. because we learned this by using alumina as a support. I have data in alumina, so we learned that's not good. So then we cannot put a magnesium oxide and silver oxide surface area equal because that's given. You will never find the magnesium oxide, silver oxide, same surface area because they are not important. What's important is the metal particle, ruthenium, on their surface. Will large better or small better? Obviously, on magnesium oxide, large particle is better because they give you lower the free energy. But on the silver oxide, they say no. If you put a large particle on my surface, silver oxide said I'm not happy. That means you have to go back to smaller particles. Did I illustrate it correctly? Clearly? Is that the model? That's the model says. Did I answer your question? Yeah, and then later on I show the data. So later on we have this is the STM data. It's called STEM. You heard about STM? It's called scanning transmission electronic microscopic. Okay, so we did this and we found out indeed magnesium oxide particles are very big, whereas on the silver oxide ruthenium particle very small. So all these catalysts are tested in here, and we have experiment data validated. We have DFT modeling to guide us to go through the small particles, and then we have the imaging characterization to show, hey, this is really that makes sense because you have no problem large particles on magnesium oxide, but on silver oxide you better go to small particles. Is that your question? I think did I answer your question on this the slide number 8?
Yes, sir.
Yeah. Okay. So yeah, thank you for the question. I'm glad you I think that you have some knowledge on the DFT work. DFT is very difficult to understand because I'm not expert on DFT, so that's why I hire postdoc to do the DFT work. But over the years, I kind of understand what's the thing behind. But I do not know how to run the DFT model, but I can interpret the result for you. So okay, so I will come back. This is going to be this cartoon will be the end of our session today. We have probably 10 minutes to go, but I still want to interpret to you and then make a point. The point is when you design microwave sensitive catalyst, you have to consider the reactor design because they go together. So in the reactor design, we have a microwave go along the reactor tube, but the microwave go along this reactor, the membrane, the tube, they heat differently. So different segments or along the lines of the reactor, they see the different intensity because of microwave, they oscillate, all right, go by wavelength. To take advantage of this, so we have to put a catalyst at a different location. That means when intensity is high, we put a less catalyst or less active catalyst. When the intensity low, we put more. So by doing so, we basically minimize the hotspot formation. Remember, ammonia synthesis is exothermic. You don't want to escalate the ammonia synthesis, but you want to minimize. In industry, Haber-Bosch, what they do, they put a heat changer in the reactor, all right? Yeah, you can do that in heat changer. But in microwave reactor, we want to do modular, the smaller the reactor. If you put a big heat, big exchanger into microwave reactor, that's no brain because that's just a waste of the microwave reactor, all right? So that's why we have to design the catalyst. We have to consider the integration of the catalyst into the reactor. And we have to really appreciate the thanks to the 3D printing allow us to print catalyst on the different segments. We can also print the reactor as well. But at this moment, we just try to print the catalyst at a different location. Then we run a microwave, different frequency, and make sure there's the resonance or the synergy. When the microwave, we change the frequency, we want to make sure different frequency, they landed on the 3D printed location. So there's a lot of work in there. So, and also one more thing, you may be wondering, how would you know different location has different reactivity? Well, there's another technique called, let me show you. Let me show you the picture, okay? Called the in situ, okay, hold on. Oh God, I lost my screen. I think I have so many things open, so I lost my screen sharing. But I want to, okay. I'm going back to here. So you can still see this, all right? So can anybody say something? Can you see my slide?
Yes, sir. Yes, sir.
Yeah. So basically, I'm trying to repeat. The microwave go around the tube, and then the microwave heat the this tube, different segment, different location of this reactor tube see the different intensity. So that means they are heat differently. So we want to take advantage of this microwave, and then we put a catalyst at a different location by concentration or by the different activity. Okay, so 3D printing will do the job. So the last question, I'm asking question, I'm going to self-answer. So can you read this highlight? So how can you monitor activity at a different location of the microwave reactor zone? Think about it for 30 seconds. I'm looking for the cartoon for you. So basically, for the reactor, you can use the gas chromatograph, GC, or analyzer, all right? You have coming in, you can have this gas going in there. But we want to monitor in situ.
So we can do thermal camera or something like that.
Could you get closer to speaker? The microphone speak slowly because there's feedback. I cannot hear you. Go ahead. Yeah.
We can have a thermal camera. We can see the intensity of the heat with the higher rate or like something. Through thermal camera.
What technique? I'm looking for a technique you can use to monitor the activity at a different location. Could you tell me any technique?
Technology can make it, but for monitoring how much heat or something like that, we don't know. But it's a halfway sine wave. We say that like it's not a full sine wave, it's a halfway sine wavelength. So intensity will be higher at the top and lower at the bottom.
Yeah.
So
intensity is high, but that means when intensity high, when they interact with this reactor tube, at high intensity, the tube will be heat hotter, and the low intensity will be heat the lighter, all right, the lower temperature. So you basically see this the oscillation I draw. Basically, your temperature distribution will be like high low high low high low. So now we are putting catalyst and then following this pattern, yeah, putting low high low high low high. You follow me? So my question, actually, I don't think you answered my question. My question is, how would you monitor the reaction at a different location? How do you monitor activity?
Water bubbles will be found at high intensity temperature.
Say it again.
Air bubbles will be formed at the high intensity temperatures and low
Yes.
temperature will be formed.
Yes, but what tools or instrumentation? What instrumentation you want to use to monitor the activity?
PFT. Instrument, spectroscope.
Yeah, I'm basic. Yeah, I think I heard somebody say the spectroscopy, which is good. Keep on going.
Spectroscope.
Makes sense, all right? So I think the I can hear the background. Someone say the in situ, the spectroscopic. Yes, you have to use. That's why I want to show you a cartoon. Actually, my laboratory, we are building that capability. So by doing so, you have to have a Raman optical fiber with the lens going into the reactor. This is a new technique, okay? So I think we still, oh my God, we are running out of time, but I still want to show you the cartoon. Give me a few seconds, I will be there. Because I have so many things open. I will do this. Okay, I will keep in mind, I don't want to hold your time. We are running out of time. So tomorrow, at the beginning, I think tomorrow day 5, is that right? Oh, tomorrow we have, again, we have 3 sessions. Yeah. So ammonia, hydrogen challenge, solution, plasma center. So tomorrow I'm going to show you in situ the technique before we go into the session. So I think tomorrow we have 3 sessions as well. So Dr. Anand will email me the links. We will talk. Okay. So it will take me time to dig out the picture of the in situ Raman I'm building in my laboratory. Okay. So you need a sensor and optic fiber will go in there. Because traditional Raman, you have a lens. The lens will not allow you to go inside the reactor. You have to have an interface going in there. So it's a very powerful tool. So we'll come back to this tomorrow, spending maybe 10 minutes before we go to the next topic. Okay. So thank you everyone. Yeah.
Thank you so much.
Yeah.
So I think you are so tired and you had 3 sessions. Thank you so much.
Yes, I'm really tired because it's from 1 a.m. to 5:30 a.m. I didn't sleep. Then I have day job from 8 a.m. I will start working. So I'm basically working 24/7. You can see. Yeah.
We understand.
Yeah. It's okay. I think there's I'm a good news is we don't have a classes over weekend. I can catch up some sleep and then we have another week to go. Yes, basically I work. It's very difficult to work, give a lecture during the night, and then I have to work during the day. So yeah, it's okay. So we'll be there. Thank you.